Good morning.
Good morning, sir.
Yeah. So in the last class, we actually discussed about frequency domain enhancement. We saw that by taking the image and also the kernel to the frequency domain, we can perform image enhancement. Uh, so let us now try to uh, go through the details further. Is the slides visible?
Yes, sir.
Okay. Okay, so what we saw in the last class is there are different spatial filters which can be converted to frequency domain filters. We started off with an ideal low pass filter. So, ideal nature means there is a sharp cutoff, as you can see, and we saw that by just using such a filter and deciding about the cutoff frequency, which is the distance from the origin, uh, okay, to the point where you are going to allow, we could see that it could remove noise and also it is blurring edges. And what we noticed in the last class is an ideal filter because of the ideal nature. The process is convolution with a sync pulse. Because of this convolution, you could see an effect here. Can somebody tell me what is that effect we discussed? Hello, somebody respond. What is that effect?
Ring effect, sir.
Ringing effect. Okay, very good. So, to overcome that, uh, we can also use a Butterworth filter. The advantage in Butterworth filter is you can decide about the order of the filter by taking a different value of n here. So the order of the filter will decide about the shape of the transformation or the shape of the transfer curve. So as you can see here, as the order of the filter increases, the curve becomes more and more ideal. So I can just play with this order and keep observing the ringing effect and ensure that blurring is or the noise removal is good, but at the same time we don't have ringing effect. Another filter which can also avoid this ringing effect is a Gaussian low pass filter. So this is the expression. So you can observe here, this is almost like a Gaussian pulse with some normalization that is taken place. So depending on the distance from the origin, by just changing the cutoff frequency, you can allow more and more frequency components. So we could see the effect here as D naught increases, that is the cutoff frequency increases, your low pass filter starts allowing more and more frequency components. And by using such a filter, you can actually remove noise, as you can see, and of course the edges are also blurred. Again, here you can observe that because of the smoothness of the transfer function, you don't see any ringing effect that was visible in ideal filter. Okay, so we also took an application. This is one of the application whenever I'm trying to do text recognition, and when there is a poor resolution text like this, which has got breaks, so I can just apply a simple smoothing filter before we go for character recognition. So Gaussian low pass filter is used in this case. So you could see that the edges are smeared, thereby there is a connectivity. So I can now further pre-process it by just using algorithms like thinning and then use it for recognizing the characters. Another good example, as I said, is in this woman image, we can probably remove this wrinkles that are seen near the eyes, which are normally there usually because of aging. So you could see that by applying a simple filter, you can just smooth it out. In fact, this is how actually photo editing is done. Sometimes when you are asked, when you are going for editing the photos, probably they do such type of processing steps. This is another example where you have an image here which has got some scan lines. I don't know whether it is visible on your screen. There are some scan lines here. So this scan lines can be removed by applying a Gaussian low pass filter of different cutoff frequencies. Okay, so just like what we discussed in spatial domain filtering, here also we can discuss sharpening frequency domain filters. So as I mentioned, sharpening can be done by using high pass filter. Uh, so a high pass filter can be obtained by subtracting the low pass filter transfer function from 1. Okay, I can demonstrate this by a simple graph. Let us go to the OneNote. Is the OneNote visible?
Yes, sir.
Okay. So all of you know that I'll just take a 1D case for demonstrating it. So a low pass filter can be shown something like this. So let me just assume that I am using a cutoff frequency FC. This is the frequency and this is your H of F, the transfer function. And an ideal low pass filter looks like this. I'm not showing the negative frequency region here. Now you also know an ideal high pass filter. Let me just take the cutoff frequency to be FC. So this is an ideal high pass filter. All of you know that this magnitude is 1. So H of F. So this is for a low pass filter and this is for a high pass filter. So what is the relationship between this? The relationship between these two is, suppose if I subtract 1 from an ideal low pass filter response, I'll get high pass filter. Correct. So if you subtract 1 from subtract this from 1, what happens is in this region 1 minus 1 is 0, that's what you see, and in this region 1 minus 0 is 1, that's what you are seeing here. So this is the relationship that we are going to use now in a 2 dimension. So let us just observe this now. Okay, so a high pass filter can be obtained by subtracting subtracting the low pass filter transfer function from 1. This is what we have seen. So this is true even for 2 dimensional also. Okay, so let us take one by one now. If it is an ideal low pass high pass filter, as all of you know, for example, in this case, in an ideal low pass filter, as long as the distance d is less than the cutoff frequency, the magnitude has to be equal to 1. That means the low frequency component should be allowed, high frequency component should be attenuated. So the reverse of that is what you get here. So observe, when the distance d is less than d naught, that means at lower frequencies the magnitude is 0, at higher frequencies the magnitude is 1. That means all the frequencies which are above d naught will be allowed, and all those frequencies which are below d naught will be attenuated. So this is just the reversal of your ideal low pass filter. As usual, because of the ideal nature, this introduces ringing effect. And you also know that physically realizing a high pass, sorry, an ideal filter is not an easy thing, because you need to definitely go for a good electronic design uh, uh, for realizing this. And because of this ringing effect, we already saw in the previous case that we can go for a Butterworth filter. So you can observe a Butterworth filter here. Now observe here, the only change is there is a reciprocal. Previous case, d of uv was on the numerator and d not in the denominator. It is reverse here. How can I verify this? Suppose if the distance d is 0, that means I am at the origin. 1 by 0 is infinity. So 1 by infinity is 0. That's exactly what you got here. So it's easy to verify that this is a high pass filter. Okay. N again here is order of the Butterworth high pass filter. So by changing n, I can change the shape of the filter transfer function, and you can go more and more ideal as I go to the higher order. Now Gaussian low pass filter, 1 minus of the high pass filter transfer function will give me the high pass filter. So you can observe here, this was the low pass filter, e to the power of, let me just show that again, the e power minus d square u of p by 2 d naught square. So 1 minus of this will be high pass filter. So easy to remember the transfer functions. So 1 minus e to the power of minus d square. So these are the three high pass filters. Ideal filter has got the same effect, that is ringing effect. Butterworth filter has an advantage because I can play with the order of the filter and make sure that the ringing effect is reduced. Gaussian filter can also remove the ringing effect. Among these two, Butterworth filter is better because you have the control over the shape of the transfer function. So I can go more closer to the ideal nature of the filter to allow or block as whichever frequency you want to allow or block. At the same time, I can just okay, go for that particular order so that the ringing effect is reduced. So there is a control here which is not there in Gaussian high pass filter. That is the difference. Both of them are helpful in removing the ringing effect, but Butterworth filter has got one more control where the shape of the transfer function can be controlled. Okay, so these are the various uh, filter transfer function that is shown as an image. As you could see here, this is the ideal high pass filter. So what you see here is actually a hollow shape. That means in this region the value is 0, all other values are 1. This is 1. Okay, so here wherever you have black, this is 0, and wherever you have white, this is 1. That is what you wanted. Wherever I have the distance d less than d naught, I want it to be 0. Other values I want it to be 1. So 1 means white and 0 means black. So this is an ideal, in fact image of an ideal high pass filter transfer function. And this is actually your 1D representation, so which I already showed you. Till the cutoff frequency, the magnitude is 0, and after that the magnitude has become 1. So ideal nature is observed here, a sharp transition from in fact stop band to pass band. uh, this is about a a Butterworth low pass high pass filter, same almost similar shape except that there is a smooth transition, as you could see here. And because of that smooth transition, you can also see the color is gradually changing. Here there is a drastic change from black to white, whereas here from black to white it is gradually changing because of the smooth nature of the curve, which can be visible, which is seen here also in the 1D plot. This is for Gaussian, which also looks similar to this, and but you don't have the control over the shape. For example, if I go to higher and higher order filter, I can try to get a, for example, if I take a very high order Butterworth filter, it almost resembles like an ideal filter, but that is not possible in a Gaussian low high pass filter. So of course some results are shown here. This is again to demonstrate the ringing effect, what you notice. Hopefully you could be seeing that ringing that is happening here. Okay, and these are the results. I don't know whether you can clearly visualize. There are some ring structures that are seen inside these alphabets. For example, just try to identify this region within the alphabet A. You could see that ringing structure, but that is not visible either in the Butterworth filter or in the uh, I think this is for different distance D naught. Okay, this is actually for ideal filter only. So there is a ringing effect here, but of course in this case it's not that visible. And observe here Butterworth high pass filter where that ringing effect you can now I think you can see the difference between the previous one and the observe the central region of this particular alphabet. You would see that in the Butterworth filter that central ringing effect is not there. Just observe that. Is it visible on your screen also? Are you able to notice the difference? Can somebody respond?
Yes, sir.
Okay. So this is for Butterworth high pass filter. There is no ringing effect. So edges are identified. This is for Gaussian high pass filter. Again, there is no ringing effect as you can see. So these are the results of the various filters on a typical image. And this is an example where we normally use high pass filter because whenever I'm trying to do uh, fingerprint recognition system, this is a raw image, a thumbprint that you normally take. But you are only interested in this edge information. Particularly, I don't know whether you can notice, okay, a point here. Okay, so these type of points where you have some, um, in fact, we call these as minutia points. So they are very important. In fact, they are the features of your fingerprint. So to get that, what they do is they'll just use a high pass filter. It's almost looking dark because the edges are very small. So after performing high pass filtering, if I just do a thresholding, wherever I have white, I'll get white pixels here. Wherever I have black, I have black pixels here. So this is now a processed thumbprint or fingerprint image which could be used for identifying the feature points in this, which can be further used for recognition. There is a small mistake here. Please correct it by yourself. Uh, I want you to identify what is a mistake. So this is the comparison of an ideal low pass filter, Butterworth low pass filter equation and Gaussian low pass filter equation. This is an ideal high pass filter. This is an ideal Butterworth filter. Ideal sorry Butterworth filter. This is a Gaussian low high pass filter. Now can somebody identify what is a mistake here? I'll leave this slide for a minute. There is a mistake here. It's a print mistake actually.
The D naught by D of U
Which
in
one?
Butterworth. First Butterworth, sir.
How? How? Can you justify?
No, sir. Correct.
This is correct. Okay. Yeah. Any other? What is a mistake?
Sir, in high pass filter, H of U, V 0, D of U less than or equal to D naught, whereas 1 for greater than D naught,
Correct.
sir.
Correct. Who is this? 097. Sindhu, is it? Okay.
Yes, sir.
Okay. Good. Good observation. So there is a mistake here. So you need to correct this because this is a PDF. I could not edit it. So I'm just leaving it as it is. But don't make that mistake in exams. So you can either change this less than or equal to greater than or equal to, or the best thing is change this. Here you make it as 0, here you make it as 1, because as long as the distance is less than d naught, high pass filter should not allow anything, so it should attenuate. This should be 0, this should be 1. Okay, good observations in. Okay, so I hope others have. I'll try to edit it and send it to you, but please make this corrections whenever you're answering. Don't repeat the same mistake. Okay, so this is just a comparison, just to have all the equations together so that it will help you to in fact compare them. So what we noticed is ideal filters are good, no doubt, because they are very good in removing the required frequencies and attenuating, because there is a sharp transition. But because of the sharp transition, the disadvantage that we have is it introduces ringing effect. Butterworth filter and Gaussian filter can take care of that. Among these two, in fact, I go with Butterworth filter rather than Gaussian, because Butterworth filter has got a control. I can control the shape of the transfer function so that I can be very close to an ideal filter. At the same time, I can take care of the uh, ringing effect. Okay, so this is a comparison which is just a gist of whatever we have discussed so far. Okay, so I think this would be the last type of filter that we are going to discuss, called homomorphic filtering. Let me just go to the OneNote. If you remember, we noticed, we just represented the gray level value that we got, okay, as a function of two things. What are those two things? Can somebody tell me? It depends on two parameters. The gray level depends on two parameters. Can anybody? In fact, I had given this also as one, probably the quiz question, if I remember. Okay, I will give you the answer. It depends on illumination and reflectance. So can you at least complete the equation? What is F in terms of illumination and reflectance? No comments.
So I cross I.
I into it, correct. It is I, that is the illumination, multiplied by or the reflectance. Okay, so whatever filtering I do, for example, if I just take this to the frequency domain, then I will be having f of uv, which will be Fourier transform of this product. Okay, so whatever filtering I do, so if I multiply this with some filter, if I multiply this with some filter, so h of uv into f of uv, what you get is the whole thing, Fourier transform of the illumination multiplied with the reflectance. This gets multiplied with the filter. That means the filter h of uv is acting on both illumination and reflectance together. But actually, the illumination portion and reflectance portion has got some relationship. Let me now go to this slide. Okay. Illumination, actually, this component is going to have the slow, that means going to capture the slow spatial variation. That means the low frequency components in the image, okay, are captured by using this illumination component. Whereas the reflectance component is actually the high frequency component. That means the abrupt variations that we have in the image will be taken care by the reflectance component. So what happens is, suppose if I have, let me just show you an image, then I think it's clear. If you carefully observe this image, I can go to the full screen mode. So if you carefully observe this image, actually this image is, okay, is captured wherein if inside this cabin, since the light that is falling will be less, so there is a variation in the, even though the external illumination is constant, that would be constant on the outside region here, but because this portion of probably this could be a machine, I believe. So this machine is kept inside a cabin, so inside this the illumination is not so much. So many finer details here would be missing when I capture the image. So you could see that there are many things that are inside which are missing. For example, observe here, this is actually a processed image. Observe here, this is now visible, which was not visible here. This region which was inside, this is also visible, and some more region inside here, hopefully it is clear to you, that is also visible. So there could be such illumination variations. When I capture, for example, when you are capturing some image, you can expect that there would be some probably a tree shade that is falling, because of which the image that is captured will have illumination variations. Now the question that we are asking is there any way I can I can filter, or I can apply this filter only on the illumination region of the image or on the reflectance region. So I don't want to apply the filter like this. See here, if I apply the filter like this filter is applied to both illumination and reflectance. So I don't have any control. The filter will in fact filter the entire image. It is not taking care of only the illumination or only the reflectance. So how do I filter only the slow variations or the abrupt changes in the image? Somehow I should make sure that I should make sure that uh, this I and R are separated out. That means the product that I have here, because when I apply Fourier transform, all of you know that Fourier transform of the product is not same as Fourier transform of the sums or the individual products. Okay, this is not true, correct? Is it correct? It is not true. I can show it in red color. Is this correct? This is not possible. Fourier transform of sum is Fourier transform, sum of the Fourier transform, that because the Fourier transform is linear. This is not true. That means if I apply the Fourier transform, it won't be applied only on the illumination or reflectance. This is not true. Okay. So now the question that I am asking is, how do I ensure, or how do I bring in a plus sign here so that illumination is separate and reflectance is separate? If that were to be the case, when I apply a filter like this, the filter separately operates on the illumination portion and reflectance portion. So I should get a plus sign here instead of a product. Okay. Can you tell me which uh, mathematical command or which mathematical expression will convert products to sum? You would have seen this making a product to sum. Anybody? Any guess? Quick guess. Not a difficult guess. I think it's. I want to change product to sum. Which mathematical tool can do that? Any guess? Okay, there is no guess. What is log mn? What is log mn? Hello, are you there or not interested to speak? What is it?
Log
Sir,
m plus log n.
It's a simple question. Why are you so lazy in answering such simple questions? Thank you. Log m plus log n. So, suppose if I apply that log operator here, what happens is, so if I take log of f of x comma y, That means I take logarithm of the image first. Then on the right hand side, I'll get log of I of x comma y plus log of r of x comma y. I have now separated them. Earlier it was product, now they have become sum. Now if I apply a filter on this, so if I apply some filter on this, h of uv into this, so what you will get is h of uv into the elimination portion, of course logarithmic of that, plus h of uv, because this is possible. Linearity property of your Fourier transform allows me to do this, correct? So by using this additional operator log, I can now separate illumination portion and reflectance portion. Now apply a filter and then decide the response of the filter. For example, if you want to only work with only slow variations, work on the illumination, that will work on the illumination portion. If you want the high frequency variation, then that corresponds to the reflectance portion. So that's exactly what we saw here. Okay, so let me go back to the slides. I think now the story is clearly understandable. Okay, so this is a very busy slide, I say, because a lot of equations are there, but not very difficult, I am sure, because all the required background I have explained. So this type of filtering is called homomorphic filtering. Please remember this. This is a very important require step actually called homomorphic filtering. Okay, so it uses illumination reflectance model, and as I already explained, F is a product of I and R. Fourier transform is not separable. That means if I take Fourier transform on f of x comma y, it will not be Fourier transform of I into Fourier transform. You know that. On the product, it is not separable. So what I do is I'll take log of f of x comma y and I call it as z. Okay. So z of x y is actually logarithm of f of x comma y. So on the right hand side, it is log of I into r, which will be log of I plus log of r. And you are taking Fourier transform on that. So it is Fourier transform on the log of illumination, Fourier transform on the log of the reflectance portion. Call this as some Fi because it is the illumination portion. Call this as Fr because it is the reflectance portion. So now if I apply a filter, since I have separated illumination and reflectance, if I apply a filter like H of UV, this filter will act separately on the illumination portion and the reflectance portion. Now I can choose the transfer function for my requirement. Suppose if I am working with only I know that there is some illumination variation in the image, okay, and so I can just carefully choose the illumination, sorry, the filter transfer function, which will work only on spatial variations or on abrupt variations and take care of it. So this is the advantage. The filter now works on separately illumination and reflectance. Once I do that, you have to do inverse Fourier transform because you have to come back to the spatial domain. So just take the inverse Fourier transform, but don't forget that you took log in the beginning, so you have to do the opposite because you have to invert or you have to reverse that operation. So if I take natural logarithm, the inverse of natural logarithm is e to the power. I think all of you know about it. Okay. Uh, is that clear? Why e to the power of s of x comma y is taken here? Any doubt here? It's the inverse of log. Am I correct? I'll explain that also if you want. It's a simple operation, nothing great. So suppose if I take ln of say some x, that means this is log to base e. This is what I have got, which is y. So if I want x, this should be e to the power of y. So this is not a difficult thing for you to understand. Log x to base e is y. So I want x now. So I have to raise to the power of e. E to the power of y will give me that. Okay, so with this I can now do that inverse operation. So e to the power of s of x comma y. So you know s of x comma is I dash plus r dash. So now it will become the product because I have exponentiated this. So it is e power I dash into e power r dash. Thereby I will get the modified illumination portion and reflectance portion separately. Okay. So this is actually the concept of homomorphic filtering. I repeat because this is a very important uh, okay, filtering technique. It works on illumination and reflectance model. Since if I okay, the image f of x comma y is a product of I and r. Just to separate I and r, you take logarithm of that. Now illumination and reflectance are separated. Apply the filter. So the filter transfer function decides whether I should work on the illumination or on the reflectance portion. Take the inverse of the Fourier transform to come back to the spatial domain. Since I have taken log here, do the inverse of it, which is e to the power, and thereby I get a processed image. And now depending on your transfer function, I can just play with only illumination or reflectance. Okay, so the whole story is explained in the form of a block diagram here. So the input image, first step is to take log of it, then apply Fourier transform on it. So I'll get Fourier transform of the log, multiply it with the filter transfer function. Then the next step is take the inverse. Then the next step is exponentiation. So log here, exponentiation here, DFT here, inverse DFT here. Okay. So I have got back the processed image here, and this is actually the block diagram approach of homomorphic filtering, which works on illumination and reflectance model. Now, how normally they do filtering is they'll choose this transfer function carefully. For example, let us take gamma L and gamma H, and if gamma L is less than 1 and gamma H is greater than 1, if you carefully observe, this is a transfer function. What is the meaning of that? The low frequency components are attenuated, because if gamma L is taken as less than 1, I am multiplying the term with a value less than 1. That means I am attenuating the low frequency components. If gamma H is greater than 1, I am increasing the, or I am just enhancing the high frequency components or amplifying the high frequency components. So as I already told you, slow spatial variations correspond to the illumination component. So if I just attenuate the effect due to illumination and amplify the effect due to reflectance, I can definitely get the high frequency components easily. That's exactly what is seen here in this image. Okay, so in this region, I am missing actually the edges here or the high frequency components. So if I choose something like this, I am enhancing the high frequency component. Thereby, in this region, I could also see this region very clearly. Okay, so inside this cabin, the regions were missing here because of variation in the illumination reflectance. So that is taken care by this. Okay, so this is how whenever you have variations in the illumination, for example, if there is a tree shade that is falling on an image and you are working on license plate recognition, if this tree shade is affecting the character recognition, I can use such type of homomorphic filtering. Okay, so this actually completes unit 2. Uh, okay, let me come back.